So it's my pleasure to introduce the next speaker, Chris Skinner from Princeton University. Chris has worked in both algebraic and analytic number theory, as well as on the Langlands program. But somehow everything he's done has also had some effect on the Birch Swinnerton-Dyer Conjecture. Celebrated result a few years ago, together with Manjul Bhargava and Wei Zhang, showed that a positive proportion of elliptic curves satisfies the Birch Swinnerton-Dyer conjecture. And I hope Chris will tell us about what happens for the rest as well as the ones already done.
Thank you, Andrew. Well, I'll leave it to the audience to see whether I've answered that or risen to that challenge by the end. Of course, it's a great pleasure to be back here at the Clay meeting, and also an honor to have been asked to give this talk, and even probably better, a nice challenge to have to think about how to give such a talk and to reflect on what has been done in, say, the last 25 years. So, my talk's going to have roughly 3 parts. I will begin by just reminding you of the problem and sort of unpacking it. And so, discussing what it's about and how we actually get to this formulation. In the second part, I'll discuss the history prior to the millennium. And then in the third part, I'll describe what's been done, say, in the last 25 years or so. So here's the problem, more or less as stated on the Clay webpage under the millennium problems. So let E be an elliptic curve over the rationals. Then the Taylor series expansion of its L function at the point s equals 1 has a form, a constant times s minus 1 to some power r, then of course those higher order terms. The interest is then that very first term. And the r, the order of the 0, is supposed to be the rank of the group of rational points on the elliptic curve. So as I said, I'm going to spend some time actually getting to this formulation, unpacking what this means. So what is this really about? So first of all, it belongs to one of the oldest themes in mathematics, the study of integer or rational points or solutions to equations. So here on the left is a 5,000-year-old clay tablet from Babylonia, and as you can see, it gives Pythagorean triples. So it's a list of triples of integers, a, b, and c, that satisfy the Pythagorean relation, a squared plus b squared is c squared. So the sides of a right triangle. And fast forwarding a few centuries, we have on the right the republication of Bachat's translation of Diophantus's Arithmetica. This is the version that has right here, the printed marginal comment of Fermat that became Fermat's last theorem. And the elliptic curves are firmly in the tradition of both of these texts. So in fact, the Birch and Swinnerton-Dyer conjecture is about the rational points on algebraic curves of genus 1. So here's an example. You can write 6 as a sum of 2 rational cubes. As on the slide, and you can think of that as a rational point on a genus 1 curve defined by the simple equation x cubed plus y cubed is equal to 6. This is what I mean by rational points on curves. So let me remind you, beginning perhaps with the work of Riemann, if you look at the complex points of algebraic curves, they form Riemann surfaces. The Riemann surfaces are organized by their genus, and so topologically, the Riemann surface is often drawn as a torus with a number of holes or a donut with a number of holes, depending on whether you're talking to mathematicians or your seatmate on the flight over. And so genus 0, genus 1 has 1 hole. So the genus is the number of holes. This topological invariant has a significant sort of influence on the solution to the equations, onto the rational solutions to equations. So I'm also going to stick mostly to plane curves. So plane curves then are just equations in polynomial equation in 2 variables. And it's from the equation, it's fairly easy to read off the genus. So in particular, the genus, say, of the equation giving the circle, equation for a circle is 0. And if I change that one of those exponents from 2 to 3, the genus goes up. As I said, the genus has an impact on the rational solutions to these equations. And so let's begin with the simplest case. All right, so I've included these words. So C is an algebraic curve, and if I was speaking properly right, I'd have to say things like projective, smooth, geometrically connected, and things like that. And that's the last time I'm going to say that. So we look at curves of genus 0. So these were the donuts with no holes, beignets, I think. The number of rational points falls into two cases. There's either no rational points, or if it has a rational point, there's in fact infinitely many. Even better, there exists an algorithm to decide which case that you're in. So you hand me an equation, there's a finite check to decide whether there's finitely many whether there's 0 or infinitely many. And you also know that as soon as you know one solution, you can parameterize all the others. And so here's the simple example for the case of the circle. All the rational points on the circle can be parameterized as written, where t runs through. So as t runs through the rational numbers, this will run through all the rational points on the circle. You have to make sense of maybe t equals infinity to get one of those points. All right. That's very special to the genus 0 case. When the genus is at least 2, so if your Riemann surface has at least two holes, the curve can only have finitely many points. This is Falting's theorem. This is a celebrated conjecture of Mordell and proved by Faltings. And it's an open problem, I think, to find an algorithm to compute these finitely many rational points. So that in itself has a lot of interesting mathematics. So that's the genus 0 case, and then the genus greater than or equal to 2 case. And the Birch Swinnerton-Dyer conjecture lives in the middle. So it's the case of curves of genus 1. So here, actually, there can be 3 possibilities. You can have no points, no rational solutions. You can have finitely many rational solutions, or you can have infinitely many rational solutions. And all 3 possibilities occur. So it's an open problem to determine which occurs for a given curve. So what is an elliptic curve? An elliptic curve is a genus 1 curve together with a distinguished point. So we allow ourselves to have one solution. So we're ignoring the case of no solutions. We're allowing ourselves to have one solution. We sort of identify it, label it 0 or O. And once you've done that, then the curve can actually be written in a very simple form. So it can be written as one of these plane curves in this form here, sometimes called the short Weierstrass form. And the distinguished point, you may ask, where is that? That's actually the point at infinity when you take the homogenization of this. It's the unique point at infinity. And this relation on the coefficients a and b is just to ensure that series of words that I was talking about, non-smooth, et cetera. Okay. Okay, so we have one rational point. So the set of rational points can be either finite or infinite. And the Birch Swinnerton-Dyer conjecture is really a refined answer to which of these alternative holds. So why is that the case? So points on an elliptic curve can be added to each other. So there's a structure on the elliptic curve of a commutative algebraic group. Very concretely, it can be this addition can be done using the chord tangent method. So you start with 2 points, which may be labeled P and Q on these slides. You form the line between those 2 points and intersect that with the curve. And so because the curve is given by this equation of degree 3, there's a third point of intersection. And the x-ordinates of those points of intersection will be written in terms of expressible in terms of the equations of the line and the cubic, and so they'll be actually summed to something rational. If p and q had rational x-ordinates, then so does the third point then, because the sum of all 3 of those numbers is rational. And so the point of intersection will have rational coordinates. So great, we've produced a third point, actually a third solution if we started off with 2. Okay, and then we might try that procedure again. But if we only have those 3 points that are on the line, we're never going to get off. We're never going to get a different line. And so first thing we do is get off the line. And so there's this reflection across the x-axis by just sending y to minus y. And now you're off the line, and you can repeat this process and ask, how many points can you get this way? And so in 1922, more or less, around then, Mordell showed that you can get all the rational solutions on an elliptic curve by starting with finitely many solutions and proceeding through this addition law. So more precisely, the set of rational points on the elliptic curve is a finitely generated abelian group. So it has, abstractly as a group, it has the shape, so it has a free part, and the rank of that free part is called the rank of the rational points, and then there'll be some finite part, some torsion subgroup. And the Birch and Swinnerton-Dyer conjecture is essentially about the rank. So the rank being positive just means that there are infinitely many rational solutions or rational points on the curve, and the rank being 0 means that there are finitely many solutions. And so this is maybe a little more refined than just answering the finite versus infinite question. All right, but how do you get a handle on this rank? So we start off with an elliptic curve. We want to answer whether the set of rational solutions is large. So one thing you can do is you can take a solution over the rationals and you can reduce it modulo primes. And one kind of heuristic way to think about this is that if you have lots of rational points, then when you reduce them mod p, maybe you get lots of rational solutions mod p, particularly as the prime varies. And we know a lot about the rational, or the solutions to mod p. The number of solutions mod p is basically p, and then there's an error term, and we know the error term is well, if you count the point at infinity, and then the error term is bounded by just twice the square root of p. And so you might look at the number of points mod p divided by sort of the expected number of points, which is roughly p. Look at what happens as p varies, maybe take the product. And this is exactly what Birch and Swinnerton-Dyer did. So they did computations in the late 50s of these quantities. And that led them to a conjecture. It first looked like this. Their data seemed to be suggesting that this product over the primes behaved asymptotically as some constant times the log of x to the rank of the curve. So if there are only finitely many rational points on the curve, this product should converge. If it blows up, then there are infinitely many. But that's not. That's not the formulation of the problem that I had on the first slide. So where do we get to the actual formulation? So they also reformulated their conjecture. One way to sort of think about that reformulation is, okay, so they were looking at this product of np over p, which if I use my formula for np as 1 plus p minus ap, you get a quantity like this. And so they were looking at a product of these expressions in primes. And if you compare that with the Hasse-Weil L function of the elliptic curve, it suggests there should be a connection. Right? So the term that they were calculating looks like the inverse of this Euler product at s equals 1. The only problem being that the Euler product doesn't actually converge at s equals 1. Nevertheless, you can make a conjecture. So this suggested the reformulation that actually became the form that's on the Clay website and is sort of typically understood to be the Birch Swinnerton-Dyer conjecture. Actually, this is kind of good. This conjecture, I should say, is equivalent to the generalized Riemann hypothesis or at least implies the generalized Riemann hypothesis for the curve. Hasse L function of the curve. So this is really two clay problems in some respects. So whereas this one's just one. They also conjectured the value of the constant that shows up in this formulation, but I'll defer saying things about that till much later. Here is from the first page of, or from the introduction of the second paper that Birch and Swinnerton-Dyer published on the Birch and Swinnerton-Dyer conjecture. And you can see down here under A, they actually put both conjectures. This zeta of gamma of S is the zeta function of the curve, which is actually very closely related to the L function. This paper, I think, appeared in print roughly around 1966. All right. So the reformulation, why? There were some problems with it, as I said. The L function, it wasn't not just that the Euler product doesn't converge for S equals 1. At the time, it wasn't even known to be well-defined at S equal 1. So they were kind of going out on the limb and expressing their conjecture in terms of a function that wasn't yet known to exist at that point, although it was expected to be there. In fact, as I said, the L function was expected to have an analytic continuation and a functional equation, much like the Riemann zeta function, so it should be defined at S equals 1. And there was a class of curves that was pointed out to them that for which this was known, the so-called curves with complex multiplication, examples of which are these very simple curves here. And for those curves, they even had a very nice formula for the value at 1. So not just was the value known, but you could write down some nice closed formulas in terms of other functions. And they could do a lot more precise calculations, and that led them actually to the conjectured value of the constant that appears in the Birch Swinnerton-Dyer conjecture. All right, and here's a picture of Birch actually saying that Ian Castles pointed out that Düring had proved that these L functions of these special curves had these properties. Fairly quickly, the conjecture was sort of absorbed by the number theory community, quickly generalized, extended to beyond elliptic curves to other other algebraic groups like abelian varieties, or even elliptic curves over number fields, or abelian varieties over function fields and the like. And the same year that Birch and Swinnerton-Dyer's second paper came out, John Tate wrote this Bourbaki seminar article, or gave a Bourbaki seminar talk, I suppose, where he described many of these conjectures and also some very important results towards them. But it took about a decade to get to the first theoretical evidence for the Birch Swinnerton-Dyer conjecture, and that came in a theorem of John Coates and Andrew Wiles, where they show that for these curves that have complex multiplication, the curves that Birch and Swinnerton-Dyer sort of looked at more closely, that if in fact the L function doesn't vanish at 1, so at the order of then the rank of the Mordell-Weil group, which is the group of rational points, is 0. In other words, there are finitely many rational points on the curve. And this was significant for many reasons, I think. This proof made use of the arithmetic of imaginary quadratic fields. That's not surprising, since the curves have complex multiplications. There's an imaginary quadratic field lurking in the background. But it also introduced the use of ideas from Iwasawa theory into number theory, which is actually ideas that involve doing sort of p-adic analysis. And I think at the time, probably most people in number theory didn't expect that to be at all related to the arithmetic of elliptic curves. At the same time, Maser proved a well-known theorem where he proves a conjecture of Ogg, perhaps also even of Poincare, about the number, what the torsion subgroup can be. And so that became fully understood. And so the rank, the question, again, the sort of whether or not there are infinitely many rational points becomes the only mysterious part of the set of rational solutions on an elliptic curve. All right, so that was the 70s. And the 80s saw two very significant breakthroughs, both of them related to something called Heegner points, which were introduced by Kurt Heegner in the 1950s and work on some old problems like the congruent number problem and things like this. But but expressed in terms that most mathematicians at the time didn't really recognize. Fortunately, Birch spent a lot of time understanding the work of Higner. He clarified and elaborated on what had been done, and generously called the resulting construction Higner points. So there's modular curves now enter the picture. So the modular curve is the upper half plane modulo some congruent subgroup, some subgroup of SL2Z. The star just means to get a compact Riemann surface, you add some points at infinity. The Higner points come from just starting with some very simple points in the upper half plane. So points in the upper half plane are just complex numbers. If those complex numbers happen to belong to an imaginary quadratic field, then the resulting point on the on the modular curve is actually defined over an algebraic field. In this case, an abelian extension of the imaginary quadratic field. That's actually quite remarkable because this is an analytic parameterization of the points, and yet somehow algebraic points are getting mapped to algebraic points. And that's very special. And hence, well, yeah. All right, so then if you have a certain class of elliptic curves that are at the time that were known to be parameterized by modular curves algebraically, and so you could take these sort of systematically constructed rational points on the elliptic curve, or on the modular curve, map them down to the elliptic curve. And so this gave you a source of possible rational solutions on your curve, and now you want to study these solutions. So Gross and Zagier proved a remarkable theorem that related the derivative of the L function of the elliptic curve to the Néron-Tate height of the Higner point. So the height is a way of measuring some of the arithmetic complexity of the solution. And the derivative, of course, is the kind of thing we'd be interested in for elliptic curves. At least this is for particularly nice imaginary quadratic fields. And then after making some reasonably good choices, you can reformulate it as just really that the derivative of the elliptic curve at 1, or at least when something called the root number is -1, is related to this height. What's important is that the height is non-zero only if the point, actually if and only if the point has infinite order. So this is telling us that that when the derivative is not 0, this Higner point is a point of infinite order. So it actually gives you kind of this analytic proof that there's a point of infinite order on the curve, if you like, or at least an analytic criterion. That was the consequences for the Birch and Swinnerton-Dyer conjecture became more clear once people became aware of this result of Coley-Vaughan from around the same time, where he gave a sort of algebraic constructions that showed that if that Higner point is non-torsion, then in fact the rank of the elliptic curve over the imaginary quadratic field is just 1. So we only need one generator. And he could get refined results that actually said the same thing for the elliptic curve over Q, again under these conditions that the root number is -1. So exactly the conditions that Gross and Zagier looked at. So if you combine the results, you get this famous progress towards the Birch and Swinnerton-Dyer conjecture. If we call the analytic rank the order of vanishing of the L function at s equals 1, which does make sense for these curves that are modular or parameterized by modular curves, then you have a sort of this statement that for a modular elliptic curve, if the analytic rank is 0 or 1, then the algebraic rank actually equals the analytic rank. That is exactly as predicted by Birch and Swinnerton-Dyer. In the 90s, there were two important results. First of all, we could get rid of that hypothesis modular from those theorems. And secondly, actually, Kato gave an important new proof of the analytic rank equals 0 case without needing to introduce these Higner points. So that gives us sort of more flexibility to study things. And there was also a lot of computational evidence. So this is from, I believe, the second edition of Cremona's tables. And you can see he's computing data. These are labels for curves, basically the conductor of the curve. And this is the Mordell-Weil rank. So here's, you're starting to see some 2s. And then this is other information that shows up in that constant C that I haven't talked about yet. But there was extensive calculations begun. And that brings us up to the millennium problems. So now I get to describe what's happened since the problems were advertised in the 2000. So instead of talking about progress by decades, I'm now going to sort of group the progress by various themes. The work of Gross and Zagier remains one of the fundamental contributions towards the Birch and Swinnerton-Dyer, and people have probed that almost to sort of the ultimate case. So it was extended largely by the work of Shou Zheng, at least on the analytic side, and then the work of Coley-Vaughan has been extended by Jan Neckevarge and a number of others. So we have now sort of the analog of the Gross and Zagier and Coley-Vaughan theorem now for modular elliptic curves over totally real fields. We're also in the point where we still have to have this modular hypothesis because we don't know that all elliptic curves over totally real fields are modular, although that progress has definitely been made on that front as well. And modular, I have a modular plus here because modular for me in this setting is going to mean that it has to be more than just associated with an automorphic form. It has to be actually parameterized by a particular Shimura variety, Shimura curve. The final version of the Gross-Zagier formula by Wan, Zhang, and Zhang fully embraces sort of a point of view that Gross introduced to this area, which is a representation theoretic perspective, that kind of connecting the arithmetic to problems about distinguishedness of representations of groups when you restrict them to subgroups. And that's been very influential. And it's been significant that, with that perspective in mind, the Gross and Zagier have been significantly generalized in something that's become known as the Kudla program and the arithmetic Gann-Gross-Prasad conjectures. And these were actually the subject of a Clay workshop, maybe about 6 years ago. There was also work on the function field case. So I said that quickly after the formulation of the Birch Swinnerton-Dyer conjecture, it was extended over other fields. And one interesting field is the case of function fields of curves over finite fields. And in this case, so these are global fields of characteristic P. And Kato and Trion proved that the Birch Swinnerton-Dyer conjecture, in this case, is equivalent to knowing the finiteness of the Tate-Shafarevich group, and only needing to know that the L primary part of the Tate-Shafarevich group is finite for at least one prime L. Now, I haven't told you what the Tate-Shafarevich group is. That's an important part of understanding this constant, and that's going to come into another slide. There's been work of proving analogs of Gross-Zagier over function fields, and very interestingly, in this case, Wei Zhang and Jiwei Yun have found an expression for all of the Taylor series coefficients of the L function, not just the leading term, in terms of heights. So the Gross-Zagier theorem sort of essentially tells us a connection between the first coefficient and a height, and they were able to find an expression for all the others. That seems to be very much, at the moment, a phenomena of function fields. We don't understand the number theoretic analog of that. Henri Darmon introduced p-adic constructions of p-adic points that are supposed to be, that should be algebraic, or they're conjecturally algebraic. So if you recall, the Heegner points came from taking a sort of a complex analytic uniformization of the curve. And you had these points in the space that's uniformizing it, these elements in the upper half plane that are really in imaginary quadratic fields. And somehow this uniformization, which a priori is just giving you complex points, under this uniformization, these points were algebraic. So that's something that was proved or is proved by the theory of complex multiplication. So Henri was looking for the p-adic analog of that. So you take the parameterization or the complex uniformization of the modular curve, and you replace in the simplest case, you replace the upper half plane with the p-adic upper half plane. So there's a p-adic analog of this, a p-adic analytic space. And you replace then the usual complex uniformization of the elliptic curve as a torus with perhaps its Tate uniformization. So this only happens in a very special case. Doesn't, in fact, will only happen for maybe finitely many primes for any given elliptic curve. And then they give a construction of a point, and that gives rise to, well, a p-adic point a priori, and they conjecture that this is actually an algebraic point, just in the analogy with the Heegner points. But now maybe that point could live in a real quadratic field, for instance, not necessarily an imaginary quadratic field. So you're looking to generalize that Heegner point construction, and they can do lots of sort of computational evidence for this. But it remains an open problem. Computers, of course, got better. So one could do many more calculations, and there's a very nice interactive database, the L functions in modular forms database. And I took this from, obviously, just from, it's a screenshot. I'm looking at the curve with y squared plus xy equals this. Its conductor is actually whatever that number is, which is, in the case of the Cremonez table, I had picked the last page of his Birch Swinnerton-Dyer data, and that only had conductors of 3 digits, and so I think that's more than 3 digits at least. So, and then you can see it spits out generators for the Mordell-Weil group, tells you what the integral points are, gives you all sorts of other data for the elliptic curve, and so. I think the evidence is pretty compelling. So that's kind of fun. Actually, I still find this quite fun to play around with when I'm looking for curves that have particular strange phenomena. There have been, back to sort of the Birch and Swinnerton-Dyer conjecture, saying, if an L function vanishes or doesn't vanish, do we actually know something about the rational points? We have some interesting results towards what's called the equivariant Birch Swinnerton-Dyer conjecture. So now maybe you're looking at, you have an elliptic curve over Q, for example, but maybe you look at the points over a finite Galois extension. It's still a finitely generated abelian group. There's an action of the Galois group of that extension on those points, and you can look at the pieces of that set of solutions that where the Galois group is acting through a particular representation. So you can look at so in particular, if you say tensor from Q up to C, your set of solutions, you have a complex vector space in which the Galois group acts. So you can think of this as just some finite group acting on that. That'll decompose as some representations of the group, and you can ask, do certain pieces actually appear or not? And so if we have such a situation where the representation is two-dimensional and odd and irreducible, and such a representation is called an Artin representation, we can look at the L function of the elliptic curve twisted by that representation. So that would be a piece of the L function of the elliptic curve over that field. And if that piece is non-zero at 1, then you can show that that representation rho doesn't appear in the Mordell-Weil group. If this were the trivial representation, then we would just be looking at the set of rational points. So we would recover sort of the usual formulation. So the equivariant part here is just incorporating this Galois action. the proof goes beyond so what's interesting about this is that the proof goes beyond Gross-Zagier. So up until sort of this point, the only really way we had to study the Birch and Swinnerton-Dyer conjecture was through the Heegner points. So these points that came from imaginary quadratic fields via the complex uniformization of the elliptic curve by the modular curve. And now we move beyond points and beyond even curves to use classes in algebraic, or actually in motivic classes that live on products of modular curves. So for example, you might take the product of three curves and then look at maybe even a self-product, would be the simplest thing, and then you can look at the diagonal embedding of the curve into the product of three curves. This gives you a class, and you can try to ask, like, how does this class contribute to the étale cohomology of the product, and then decompose that product in ways that see the elliptic curve and maybe these other representations. And so this sort of moves beyond just modular curves. And so there's more. There's been additional results in this direction, but by Darman and Victor Rotger, and by a student of Darman and a student of myself, Fournier and Jiarong Jin. And now, okay, so that's everything I've said about the Birch Swinnerton-Dyer conjecture has been about going from something about the L function, the vanishing of the L function, or the non-vanishing of the L function, or the non-vanishing of the derivative, to information about the Mordell-Weil group. But the conjecture, of course, predicts that that information goes both directions. And so there's also been a body of work that studies this problem. So suppose the rank of the elliptic curve is known to be larger than 1. So you write down an elliptic curve, you see that you have a point of infinite order. That can easily be checked computationally because we know what the torsion orders can be, for instance. So suppose we know that we have a point of infinite order, we would expect that the L function actually should vanish to vanish. And if we actually knew that the rank of the elliptic curve had what was greater than 1, then we can conclude from Gross and Zagier and Kolyvagin that the order of the vanishing of the L function has to be greater than 1. But what about the case of 1, for instance? Or what about the actual equality of the ranks? So in particular, if the order of vanishing, or if the elliptic curve only has finitely many points, then we expect the L function to not vanish. Can we prove that? If the rank of the elliptic curve is 1, we expect the order of vanishing to be equal to 1. Can we prove that? And unfortunately, the answer seems to be no, but we can come close enough to show that happens for most curves. How do we study rational points on elliptic curves? Through something called Selmer groups. And I promise that this is the only time I'll have a commutative diagram on a slide. So you want to study the rational points, which we know is a finitely generated group. And we can look at the group modulo n. That's now a finite set. In fact, the first step to proving that the rational points form a finitely generated abelian group is to prove that this quotient is finite. Not enough, but it's the first step. This can be, and the way one even studies that at that point is to realize it as a subgroup of another group called the Selmer group, which can be interpreted in terms of Galois cohomology. And the difference between that Selmer group and the group that you're really interested in is this thing I was calling the Tate-Schaffer-Rabich group. Now, these all have, being Galois cohomology groups, they have the sort of the beneficial feature of being, you can interpret them in many ways, and that lends them sort of to an easier, perhaps, analysis. So you can often tackle the size of this group, or at least bounds on it, through studying more traditional objects in algebraic number theory, or you have interpretations of things like the Tate-Schaffer-Rabich group in terms of algebraic geometry and so. And the nice thing, of course, is that because of this injectivity, the Selmer group, the size of the Selmer group provides an upper bound on the rank. So if you wanted, for example, just to prove that a curve had rank 0, if you could prove that the Selmer group for some n was 0, then you would be done, that your curve would have to have rank 0. This group, the Tate-Shafarevich group, as the name suggests, was studied by Tate and Shafarevich, and then certainly defined by them. And then Castles showed that if the group was finite, which is conjectured by Tate and Shafarevich, then it's a square. In fact, it's isomorphic to a sum of two finite groups, two copies of the same finite group. So its order would also be a square. So it's finite, but it's also actually a square order, or even square shape, and that's important for guessing some conjectures. This is very much an open problem, and I suspect, perhaps as that top line might suggest, that you cannot, or you have difficulty separating the Mordell-Weil group, the group of rational solutions, from the Tate-Shafarevich group. And I would imagine that to prove the Birch Swinnerton-Dyer conjecture, you're going to have to prove that the Tate-Shafarevich group is finite. So let's guess some things from our this exact sequence. In the simplest case where n was a prime number, we're just looking at vector spaces over Fp. So in fact, if we look at our two expressions over Fp, then we get we can derive some expectations from what we know. That if the Selmer group, the P Selmer group is 0, so it's the object in the middle, then of course everything, the other two pieces have to be 0. In particular, the Mordell-Weil group would have to be finite, and we would expect non-vanishing. So you might ask, if you know that the Selmer group is finite, can you prove that the L function doesn't vanish at s equals 1? If the Selmer group had rank 1, and the torsion part wasn't there, then because the Mordell-Weil, or the Tate-Shafarevich group is expected to be a square, this would have to, if it were there, it would have to contribute a dimension at least 2. So the only possibility then becomes that the elliptic curve has to have a rank. So you can ask if the Selmer group, the mod P Selmer group has dimension 1, then you expect that the rank of the elliptic curve to be 1 and the order of vanishing to be 1. You can ask, can we prove that? And you can also ask, well, so if you compare what's going on again, so the Tate-Shafarevich group is supposed to have even dimension. So we can, if we talk about just the parity of the dimensions, we can ignore it. And so the dimension of the Selmer group should have the same dimension as EQ mod PZ. And in particular, if we combine that with the expectation of the analytic rank being equal to the rank of the Mordell-Weil group, you would expect that the analytic rank should be congruent to the dimension, have the same parity at least as the dimension of this group, mod 2, I guess. All right. Well, it turns out we can actually prove most of those expectations, maybe with some mild sort of technical hypotheses on the particular elliptic curves that they apply to. So this combines much of the work that's been done on the arithmetic of elliptic curves for the last 25 years. And in particular, it uses not just, say, cycles, higher dimensional cycles on varieties, but it makes use of automorphic forms on higher dimensional groups. It makes ways of bringing in the analysis of Eisenstein series, for example, on groups beyond GL2 and the like. It uses, it's very much, these are very much p-adic proofs. The p-adic world allows you to sort of link the algebra, so that's, p-adic stuff is very much algebraic, with the analysis through p-adic L functions. And so the values of the L functions arise through the p-adic L functions, which are p-adic interpolations of the values of the L functions of modular forms and elliptic curves. And so these are very much p-adic proofs. So recall, the theorem of Gross-Zagier and Kolyvagin told us that if we have an elliptic curve whose analytic rank is 0 or 1, then its algebraic rank is also the same as its analytic rank. And what I didn't tell you is that Kolyvagin actually could also show that the Tate-Shafarevich group was finite in these cases. So we do know Tate-Chapman-Ravitch group being finite. And when you combine that with what we can do in the other direction, you can produce statements that look like this. If you have an elliptic curve over Q, then the analytic rank is 0 or 1, if and only if the rank of the elliptic curve is 0, 1, and the Tate-Chapman-Ravitch group is finite. Okay, it's not quite what you would hope. I mean, the Birch Swinnerton-Dyer conjecture shouldn't really include that finiteness of the Tate-Chapman-Ravitch group, but as I said, I don't think you can avoid it. So this combines the other direction, so the direction not covered by Gross-Zagier and Kolyvagin combines, as I said, the work of many people on the problems that I was just talking about, on Selmer groups. What else do we know? This work has consequences beyond, maybe a little bit beyond sort of the actual conjecture of Birch and Swinnerton-Dyer. So Manjul Bhargava and Arul Schenker proved in around 2014 that the average order of the Selmer group for a prime p, at least for p equals 2, 3, and 5, is p plus 1. And so, of course, the average order is telling you something about how that dimension is behaving. And from this, one is able to deduce that the average rank of elliptic curves is bounded, and that's when you order the curves, say, by the size of those coefficients, a and b, in some natural way. So that was sort of conjectured to be true, but even the numerical data at the time was sort of not quite convincing. And so this was a very striking result, that the average rank is bounded. It shows that a positive proportion of elliptic curves have both analytic and algebraic rank equal to 0. That comes from showing, well, you get a positive proportion of them it turns out have dimension, or have order actually just 1. And so if you combine that with those converse theorems, the opposite direction to Gross and Zagier, you get the analytic rank being 0. You also have the results in rank 1. And in fact, by studying more closely what's going on in those average families, you get this result that Andrew alluded to in the introduction, that most elliptic curves, E over Q, are covered by the Gross-Zagier-Kolyvagin theorem. Most is sort of maybe not the important part here, because that has to do with the way you're doing your counting. And what it really is true is that for any sort of natural way of counting, we can say that there's a positive proportion for which the birds are covered by the Gross-Zagier theorem. Okay, so we're still not really getting beyond Gross-Zagier. We're just saying that happens most of the time. Alex Smith, a few years ago, proved that if you have an elliptic curve, then 50% of the fundamental discriminants are such that if you look at the quadratic twist, so this E of D is a way of twisting the elliptic curve by that discriminant. So in terms of the coefficients, you just replace the y squared by d times y squared. So it's a very simple change to the curve, but it can change the arithmetic. But 50% of them should have basically rank 0, this sort of algebraic Selmer rank 0, and 50% should have a Selmer rank of 1, which then, if we believe Birch and Swinnerton-Dyer, would say that 50% of the corresponding elliptic curve, or L functions, vanish to order 0 or order 1, which was a famous conjecture of Goldfeld. But we can't. So this is the algebraic sort of analog of that conjecture of Goldfeld. And maybe the version of this that I'm most familiar with, you would assume also that the elliptic curve had full rational two torsion, but I believe he's extended it to other cases. So maybe I need to state that a little more carefully. All right. What else has been done? I said that the Birch and Swinnerton-Dyer not only conjectured something about the order of vanishing, but they conjectured a value of the constant that appears. And that constant, well, not surprisingly, involves the Tate-Chapman-Ravitch group. The order of the torsion subgroup, the R of E, has to do with the regulator of the Néron-Tate heights of the generators of the Mordell-Weil group, and then there's a geometric, sort of finite geometric correction term there, and then a transcendental part having to do with the period. It's a beautiful formula. It's at least superficially looks a lot like the class number formula of algebraic number theory, and has been the inspiration for a whole vast zoo of conjectures about special values of L functions. We can actually prove much of the BSD formula in the cases covered by the theorems I've talked about. So here's just an example. So I look at a particular curve, 46A1, in the labeling of the L functions in modular form database. Then one can show that there are infinitely many square-free integers m such that the quadratic twist. So I would place, well, in this formula, this is the minimal Weierstrass equation. They're short, long, so it's harder to just say what's happening when you do the twist, but you change the coefficients a little bit depending on m. The L function of the twist doesn't vanish at 0, and in fact equals the value conjectured by Birch and Swinnerton-Dyer. So this is, I think this is the first time we can say that there are infinitely many non-CM curves for which the full Birch Swinnerton-Dyer conjecture holds, for instance. And the proof of just this sort of simple, sort of not, this doesn't seem like very many curves, just proving this combines pretty much everything that we've done for elliptic curves and the Birch Swinnerton-Dyer conjecture up to today. All right, I will stop there, except I will list some challenges. So by the time we have the next Clay talks on these, I challenge someone to answer one of these problems. I won't go through them all, but in particular, I've listed them maybe from most doable to well, most interesting. And finally, I would like to say that it's been a pleasure the last 25 years to at least get to peek over the shoulders of Birch and Swinnerton-Dyer into this beautiful landscape. Thank you.